Hello everybody. This video is the third in a series of videos on RC circuits that I'm creating for my AP Physics C Electricity and Magnetism class during the spring of 2020. If you watched the last two videos, what I did was create a few RC circuits using an online circuit simulator from the fet.colorado.edu website. And in the first video I had a simple RC circuit with a resistor and a capacitor in series. And I looked at the transient behavior of that circuit, and we calculated values at time 0 when the switch was closed and after a long time after the switch had been closed. And in a follow-up video, I looked at an RC circuit with an auxiliary resistor in parallel across the capacitor. And again, I conceptually looked at values for voltage drops across the different circuit elements and current at different points in time. And I did it without all the complex mathematics that's used to derive the actual functions for current and charge across the capacitor as functions of time. In fact, the only math I used was simply Ohm's law, delta V equals IR, which we will simplify in this video to just V equals IR, just to avoid having to write the delta symbol all the time, and Q equals C delta V to model the charge across the capacitor. Again, I'm going to write that as just Q equals CV. That's pretty much the only thing that I needed to take a look at. In this video, though, I'm going to extend the idea, and what I'm going to do is first look at a charging RC circuit, and I'm going to attempt to actually derive the behavior of that circuit as a function of time. And so we'll do some math. It's a simple differential equation. It's separable, first-order separable linear differential equation. We'll solve it, and we'll wind up with a function so that we can calculate both the charge on the capacitor at any moment in time and the current in the circuit at any moment in time. And then I think in a follow-up video, I'll take a look at a similar situation with a discharging capacitor. All right, so we'll take things one step at a time. Anyway, I want to start off by just saying the results of what I'm going to do are known, right, and they're readily available. And so I'm just going to state them right now before I actually go through the proof of why these are what they are. And so I'm going to kind of just tell you that if you want to know the current at any moment in time after this switch S up here gets closed, you can, and there is a function that models that. That function is I naught e to the negative t over RC, where of course e is Euler's number, right, or the natural base exponent, whatever you want to call it. And the current as a function of time follows exponential decay. If we were to graph this I versus t, like so, in the circuit that you see above, what we'd find is that this current began at a definitive value that I'm calling I naught in this case, and would decay over time asymptotically to approach 0. So on and so forth, okay? And that I naught is actually very easy to intuitively determine, because when the switch is first closed, there's no resistance across here at all, really ever, but at the moment when the switch is first closed, the only resistance in the circuit is all represented by this resistance here, R, assuming that there's no internal resistance in the battery or in the wires and so on and so forth. And so we know that the current initially at time 0 is simply this EMF of the battery divided by resistance R, like so. And so we could replace that in this equation here if we wanted to, right? And that would be the result. Now, I state that without proof. You have no reason to believe that. I'm going to prove it in a few minutes. Why is this function what it is? Okay. And also, while we're at it, if you wanted to know the charge on the capacitor, Q, as a function of time, we also have that. We can write it as C times epsilon, the EMF of the battery, times the quantity 1 minus E to the negative T over RC. And we can take this one step further, since we know from this equation up here that Q is equal to C times V, this being the voltage across the capacitor now. Then if you wanted to know, that implies that V of t, the voltage across the capacitor as a function of time, is equal to simply battery EMF is 1 minus E to the negative t over RC. Okay, so you really have these 4 relationships that are worth noting. This one, and this one. And I do highly advise my students to memorize these, even though most questions that you get asked on the College Board's exam in May will ask you to derive these or simply won't require that you really know them. I think it helps. One of the reasons being that these very same equations are also models for or operative in other circumstances that come up in the course. And in particular, if you're watching this video and you're thinking back to your mechanics course that you took probably a semester ago, you probably will recognize these. You've seen them before. The very same mathematical functions have come up in the study of air friction, a force that is proportional to velocity, at least if you studied the version of air friction where you have that the air friction force is proportional, negatively proportional to some constant times the velocity. Not this, not high friction drag. This yields a different result. But if in fact you're working under a linear air friction force model, where force is a function of velocity and is proportional to the negative velocity, then you actually get mechanics functions for the acceleration as a function of time, a as a function of time. That looks just like this one over here. You get something to the effect of g times e, and then there's something up over here. It's either b over m times t, or maybe it's m over b times t. I'd have to go back and look at that. But it's some variant of that where b is the constant of proportionality in the air friction force equation, and m is the mass of the object that you're dropping. So if you're standing on the top, say, of a tall tower, and you drop an object and it's subjected to by this downward force of gravity mg, and an upward force of friction bv, such that the net force on it, which is equal to ma, is mg minus bv. You can write a little differential equation for that, dv dt over here. When you go through the steps of solving that differential equation, you get math that's incredibly similar to this, albeit with different constants thrown in. And the velocity as a function of time, you might realize, follows this type of a graph that you see right here, right? Sort of what we call a rising exponential. So anytime you have this type of behavior here, 1 minus e to the negative t, something like that, you wind up with a curve that looks like this. It starts here at 0, and it climbs like so, and it asymptotically approaches some value up here, which of course for air friction we call the terminal velocity, right? And you can see that obviously by looking at the results here. If you were to plug in t equals 0 into a function of this type, 1 minus e to the negative t over rc, plug that in there, this whole thing becomes 1, and you get 1 minus 1, and of course the whole thing is 0, and that's why this graph starts here. And then as t goes to infinity, you lose this entire second term, right? This just becomes 0, e to the negative infinity approaching 0, and you basically just get, you're approaching this value here, in this case the EMF of the battery, in the case of air friction the terminal velocity. But the point being, these functions model quite a bit that comes up in a physics course, an introductory calculus-based physics course. So I do encourage students to memorize them simply because you're getting more bang for the buck than you are with just capacitors. Right? If you were studying magnetism, you'd also find that inductor circuits with resistors and inductors had a similar type of transient behavior that followed the exact same mathematical functions as these. So you're getting air friction, you're getting RC circuit behavior, and you're getting inductor resistor behavior, all in the same type of mathematics. So again, when I say it's worth memorizing these functions, I mean it, right? But back to the topic at hand, which, air friction aside, I'm really just interested here in deriving these results. So I'm going to clear some space here. And let's take a look at where this all comes from and how we get these results. All right, so I'm going to leave the final results up on the board on the screen here, but let me get down to the process of actually deriving them. Okay, where does this come from? So as you remember in mechanics, all situations where we're trying to derive velocity as a function of time or velocity as a function of position, have to start with some basic principle. We often start with net force equals mass times acceleration. Sometimes we start with the conservation of energy as our approach. Sometimes we prefer to start with the impulse-momentum relationship. In the case of circuits, such as this one, the operative starting point is, believe it or not, Kirchhoff's loop rule. The loop rule is the place to begin to analyze a circuit such as this one. And so that's what I'm going to do. And I want to stress, I've said this before in other tutorials I've made about Kirchhoff's laws, but I want to stress the fact that when you're doing this, when you're analyzing a circuit with the loop rule, the loop is a tool. It's an invention that you bring to the table. The actual way that you draw the loop has nothing to do with the direction of current flow in the circuit, even whether or not there is any current flow. You can always analyze a circuit, even an open circuit such as this with a switch open, using Kirchhoff's loop rule. So the loop doesn't have to correspond to the actual current flow. All right? And to give an example, if I were to just kind of apply that concept right here, right now with the switch open, let's use Kirchhoff's loop rule to analyze this circuit for an open switched RC circuit right here. The capacitor is uncharged and the switch is open. Okay? What do we see if we do that? So starting at the battery here, let me just write up top here, open switch, uncharged capacitor. Uncharged capacitor. Okay. So what will we see? Well, if we begin here, we have to pick a starting point, right? So if we begin at this location right here, and Kirchhoff's loop rule says the sum of all of the voltages around any loop has to be equal to 0. So we'll write that as follows. So if we start here at this location, and as we traverse the first leg of our loop, we walk in this direction from the negative side to the positive side of a battery. We first encounter a rise in voltage of plus that, epsilon, the EMF of the battery. Okay. Then we come across the switch, right? And we encounter some voltage difference across the switch. In this context, I'm just going to assume that it's a drop, and I'm going to write it as V sub S, or delta V sub S. Okay, then we come here across this resistor, and we realize, well, there could potentially be a drop in voltage across the resistor. And then we come across here, and we traverse that, and we realize, well, there could also be some voltage drop across the capacitor, and that's all going to have to equal 0. Again, the switch is open at this moment in time. So remember, there's no charge across the capacitor as well. So I write that statement, and now when I take a step back and think about it for a minute, I realize that, first off, this is 0, isn't it, right? Because there's no charge on that capacitor. I said it was uncharged, so there's no potential drop there. And since the switch is open and no current can flow, I is 0. So that means this is also 0. And so I wind up coming to the conclusion that the voltage drop across the switch is equal to the voltage drop, or the voltage rise across the battery, the EMF of the battery. Right? So here I have a circumstance where I've actually learned something very significant. I've actually determined the difference in potential between 2 points of an open switch in a circuit. There's no current flowing, and yet I used Kirchhoff's loop rule for a circuit with no current. Right? Totally legit. I can definitely do that. It's still true, even in this circuit in which no current flows, that the voltage rises and drops around this path that I've made, even an open path, has to always sum up to 0. And I can come to that conclusion, which is not particularly helpful for this problem, but it is just a setup, right, to lead us into what we're going to do. So now, that's prior to the switch being closed. But let's close the switch. Let's actually take this here and throw the switch here into this position so it's actually closed. And now current can flow. All right, so we're just going to write switch closed. What happens? All right. Well, the exact same equation holds true as I have above. This statement is still true, although I don't have necessarily the same quantities defaulting to 0. I still have the EMF of the battery. I still have maybe a voltage drop across the switch. I don't actually, but I'll put it in for the time being. I still have the voltage drop across the resistor, and I still have the voltage drop across the capacitor. Okay, and those all must equal 0. Now, if the switch is a perfect switch and has no internal resistance, it's a little segment of wire, and the wires in the circuit are imagined to be perfect. So the switch is closed. There's no resistance between point here and point here. If that's the case, once current is flowing in this circuit with no resistance between these 2 points, there's no voltage drop between these 2 points. And therefore, this goes away. Now, there is a current flowing, so there's a voltage drop across the resistor, and there is charge on the capacitor. At least there will be as time goes on, right? There may not be instantly, but as time passes, charge will build up on the capacitor, and so I expect to see a voltage drop across the capacitor according to this equation right here. As Q goes up, the V across the capacitor will rise. Okay, so I leave those terms in the equation, and I can substitute to simplify things just a little bit. So I leave that in there. Here I write IR, right, by Ohm's law. So I'm just taking this, plugging it into here, and then I say minus, and for the voltage drop across the capacitor, I just put Q over C. Q over C. And I say, well, you know what, that's all going to equal 0, just like that. That's my differential equation, and that is what's going to lead to all of the things that you see at the bottom here, circled in red. Now, it may not be obvious how that happens, but that's the starting point. And that is the most important point. So if you're taking the AP Physics C exam in May, and you have a question about, where do these come from? How could you derive the transient behavior of the circuit? This is how you can do it. You write Kirchhoff's loop rule, the loop rule for the circuit. I don't care if you can solve this all the way to get from this step to here. It's nice if you can. Usually it's worth a couple of points on the exam, but to be honest, this is the most important thing, getting to the point where you can write down an equation that could be used to solve for these things right here. Right? But I'm actually going to go through the steps of doing it because it is valuable, and I do believe in knowing how to do this. I said this was a differential equation. It may not be immediately apparent to you why. I don't know that I see any derivatives in here yet, but remember that the definition of current is rate of change of charge with time. So that's how we're going to get it. All right, so we're going to write this as big epsilon minus R dq dt minus Q over C, and that's all equal to 0. There's our differential equation. All right, this is a first order differential equation. It's linear. Q appears here. It's linear. It's not Q squared. It's first order because it's first derivative, right? It's homogeneous, meaning you could set it equal to 0. And it turns out it's separable. You can separate the variables in this equation and solve it by direct integration. You have done, if you've taken any calculus course, you have solved equations like this one a couple of times when you study differential equations for the first time. Now, the algebra is the hard part. The calculus is the easy part, but kind of manipulating this thing to get it into a frame or into a structure, where you can actually do the integration is where things get a little bit, just a little bit annoying. All right, so let's go through some of that. Let's go through the process right now. I'm actually going to switch colors and just go back to black to make it easier to see. So let's put a little bar here. So how do you solve this equation? How do you get from this step right here, which is the differential equation, or the diffie Q, right? Some people say that, some people say, right, diff EQ. Right, that's the result of Kirchhoff's loop rule. How do you get from there to any of these red boxed equations over here? All right, so here's how I'm going to approach this now. So I'm going to try to rearrange this equation and write it such that I have the left side just written as dq dt. So I'm going to start, so starting from here, how would I do that? So let's rearrange it a bit. Let's negative r dq dt minus q over c equals negative capital epsilon, like that. And then we'll bring this negative term over here to the other side. And I think at the same time, we'll flip the order of the terms as well. Okay, so this, I think it will become dq over dt. We'll leave the r there. Equals. This is going to become positive, right? I'm getting rid of this negative sign here. This would become positive when it comes over here. I'm going to make it negative now. Q over c. And then I'll divide by r on both sides. Like that. So it's this minus q over rc. Now, I've spoken before in a couple videos about the rc constant of a circuit, which you see appearing in these denominators of these exponentials, these exponential terms here. You can see rc, it's everywhere, right? Here it is already, rc, the rc constant of the circuit. It's starting to take form already at this point in time. Well, all right, so I've got the equation in a form that hopefully is a little bit easier to solve, to integrate. At this point, I'm going to cross multiply by dt. I'm going to put the dt on the other side, and I'm going to take kind of this term and divide by it on both sides. So I wind up with this dq over, and I have a bit of a mess on the bottom. I have epsilon over r minus q over rc. And then on the right-hand side, I just have dt, 1 times dt. Okay? So again, the algebra is really the only thing that makes this difficult in and of itself. It's not that the calculus is rather straightforward. So I've got the equation properly separated. I've got on the left-hand side I've got q dq. On the right-hand side, I've got the other variable, the independent variable, which is in this case is time. And so at this point, I can integrate. And so I'll do that. I'll drop integral signs on both sides of the equation. I'll put one here and put one here. Now we can do this integral a couple of different ways. One way you've learned to solve these equations, probably this is what you're more familiar with from your math class, is to just kind of do indefinite integrals, and then use an unknown constant as a result, and then do an initial value problem later on to try to figure out what the value of the unknown constant is. Often in physics, when performing integrations like this, it's nicer to just do definite integrals. And if we're going to do that, we just kind of have to think intuitively about what the limits of these integrals are going to be. In a sense, what we're about to do here is solve an initial value problem simultaneously with doing the integral. And so in order to do that, I'm going to think creatively about the fact that I start out with, since I'm integrating dq on the left-hand side, I start out with a charge of what? And since I'm dealing with a situation where I'm closing the switch and charging the capacitor, I'm going to say, well, I start out with a charge of 0, right? And some people want to write q equals 0. Or, sorry about that. Q equals 0, right there. And we're going to integrate to a final charge of what? And since what we're seeking ultimately is this function q of t, I don't have any definitive value that I'm going to want to use, so I'm just going to let it be q. Now, math types are going to get really upset about this, and they're going to yell and they're going to scream that I can't use as a limit a variable that's the same as my variable of integration, that I should put some kind of prime on here if I'm going to do that, just to kind of distinguish between these two. I get it. Oftentimes, we don't bother to concern ourselves with that when we're solving these things in physics situations. So I'm going to leave it alone, and math types can get mad and yell and scream at me. But yeah, right? So from q equals 0 to q. And then on the right-hand side, from 0, or from t equals 0 if you really want to put that, to t. Again, I know I should really put the prime there. And those are the integrals that we have to do. And what I'm claiming is that if you go through the process of and I will in a moment, if you do this integration on both sides, you do wind up with this function that you see right here in the bottom left in the red box. All right, so how does that work out? Well, let me see if I can make a little bit of room. I'm going to scroll over here and make some more room. All right, here we go. So the integral on the right-hand side is super simple. The one on the left-hand side is a little bit more complicated. Technically, it should be done with u substitution, where you want to let u equal what you see in the denominator. I'm just kind of just do it and kind of work it backwards. We'll just do u substitution kind of in my head and suggest that this is going to be the natural log of what? E over r minus q over rc. I still have limits to deal with. We'll put those in a minute. And then times RC, I think. Right, now you're wondering, like, well, how the heck did you do that? How do you know that that's the answer? Well, look, I mean, if that is the function, if that is the result of this antiderivative here, this operation, then it should be true that if I take the derivative of this, I'll wind up with the integrand again. I should wind up with what you see here in the denominator if I take the derivative of this. Let's try it. Let's take the derivative of this expression here with respect to q. I'll do that in another color just so you don't get confused. All right, so we'll do that in yellow, kind of right here. All right, so let's do it. Let's differentiate with respect to q. So I'm going to have negative rc, right? It's going to go along for the ride. Now I'm going to take the derivative of the log of something. We know the answer to that. So the derivative of the log of anything is 1 over that thing. So 1 over e, or epsilon over r, minus q over rc. But then I have the chain rule, right? Don't I? I take the chain rule. So I have to differentiate this piece in here. I still have to differentiate the function negative q over rc. And that's going to give me, when I differentiate that, a negative 1 over rc for that derivative. And so this is going to cancel here. The negative is going to cancel with a negative here, and I'm going to be, oh, look at that. Yeah, there it is. Yeah, I'm left with this piece right here, which is the denominator here that I have. So in fact, this does appear to work. Now, if you want to do that step by step instead of taking, just kind of jumping over it, then what you would want to do, as I said, is just kind of come up with a u substitution. Let u equal this denominator here, like so, q over rc. And then you'd have to go ahead and decide, what is du, dq, and so on and so forth, and move from there. So if you want to try that with the full u substitution, by all means, go for it. I think at some point, when you do enough of these problems, they get to be sort of second nature, and you can just kind of see your way through how to do the integration. So that's, I'm going to leave it at that. All right. So let me go back, and here we are. All right, that's an R. RC, like that. My limits, again, are from 0 to q. And you got to be careful with these limits. You can't throw away the 0 like you often do with polynomial antiderivatives. That's going to matter with the log here. You're going to have to think about that, plug that in. I'll take care of that in a minute. All right, so on the right-hand side, this is easy. This is just t, 0 to t, and that simplifies. The 0 just goes away. All right, on the right-hand side, what happens here? So we have negative RC. Actually, I think in the interest of making this simpler, I'm going to bring that to the other side of the equation just to clean it up a bit. And I'm just going to have this be the log of, we'll plug in the q, so we get this over this, minus q over RC, right, minus the log of, and then I plug in the 0 for q, and I get this. And some of you are screaming about the lack of an absolute value sign here for the natural log. I know. Over here we have negative t over RC, because I brought this negative RC over to the right-hand side, divided by it, and then I plug in the upper limit, I plug in the lower limit, but it's 0 anyway. Okay, so we're there. And then I'm going to simplify my left-hand side just a little bit. I have the subtraction of two logarithmic terms. I can rewrite that as the log of the first one over, or divided by the second, like that. And that's equal to negative t over RC still, right? So now I have a function that would be very easy to solve for t if I wanted to. I could have t equals something in terms of q, but I don't want that. I want q of t. I want what I had before, q of t equals, I normally think about time as being my independent variable, right? And so it'd be much nicer to have the equation in that form. So although technically I have it already, it's more useful to me in the other form. So I'm going to get rid of the natural log, as we kind of say in class jokingly. I'm going to e it. I'm going to e both sides, which is not effectively what we're doing, but we're simply using the inverse function. So if I simply take e to the log of all this stuff up here, like so, equals e to the negative t over RC, like that. These two functions are inverses of each other. They'll kind of undo each other, right? And so what I'm left with is simply over that equals e to the negative t over RC. Okay. And then, let's see, I can kind of cancel some things, I think. Yeah, I probably could, let's see, the first thing that happens is that this r drops out of every term here. I just sort of multiply both numerator and denominator by that, and that goes away. I can take this EMF of the battery and multiply both sides by it and put it over on the right-hand side if I want to. That lets me write this as this minus q equals this, like that, right? And then just kind of just moving a couple of steps ahead, right? I can take this as a negative q equals that, like that. That's an RC, sorry. And then subtract this like that, and then simply switch the signs. So write q equals, and this is going to be that epsilon becomes positive. I'm going to get a minus epsilon e to the negative t over RC. And then if I factor that out, if I take out that EMF term like that, this simply becomes the EMF times the quantity 1. Here we go, minus e to the negative t over RC, like that. And there you go. That's a t right there. And again, I probably should be writing this as q of t because it is a function, right, of time. A little nicer to see it that way, is e to the negative t over RC. And there you have it. That result right there that I had half an hour ago when I told you I stated it without proof. But that is an expression for the charge across the capacitor, although I have made a mistake. Somewhere there is a mistake because this can't be correct. This is a charge and this is a voltage, and they don't have the same units. So I must have dropped a C somewhere. I'm realizing if I go all the way back, let's see. It's this guy right here that I lost somewhere in translation. So what happens to that C? Let's see. It's Q over C. So I can substitute that. So this is going to have to be a C is going to have to be here. There's going to have to be a C here, like so. That's going to put a C here, much better. It's going to put the C here, and then it factors out, and so we have it right there. So finally the result is not exactly what I had, right? It's going to get rid of that. There it is. So it's going to equal the capacitance, there we go, times the EMF of the battery, times 1 minus e to the negative t over RC. So there you go. Even I made a mistake while solving this. I just kind of lost that little factor down there, but that's important, okay? Now, that's a lot of work to get from this point here. Remember, Kirchhoff's loop rule gets you the differential equation. When you solve it, you wind up with this expression right here. So it's up to you whether, you decide whether it's worth it to go through all that trouble or not. But if you want to be able to actually calculate the actual charge on the capacitor at any moment of time after the switch is closed, you need this particular function. Okay, obviously, for the previous videos, we didn't need it because we were only looking at when time was 0 and when time approached infinity. And you know what? This actually works in that context, right? We can plug in the 0 and it makes perfect sense. We get a charge of 0. We can plug in infinity and we get a charge of c times the EMF of the battery. So these functions completely work at these extremes. And actually, that's a really nice way to check when you're doing physics. You get done with some long derivation. It's a really nice way to check if you think you've done it right. If your result that you come up with over here doesn't correspond to conceptually what you know the answer should be when you plug in a 0 or you plug in an infinity for time or some such thing, then you've made a mistake. Your function can't be correct if it doesn't match the reality of what you know has to be the case. Okay, so this does work out, and so I've got Q of t. Now, if I wanted to get I of t, which was the other expression, so if I wanted this here, like so, as a function of time, then what I really need to do is take the derivative of this. I need to do this. And that's an easy enough process that I'm just going to kind of skip over it and tell you that when you're all done, what you're going to wind up with for I of t is this guy right here. That will be the derivative of this. And I think you can kind of see why. If you just kind of distribute this first thing here and take this factor and distribute it through and take the derivative, you'll see that it does end up working out to be this right here. All right, so a little bit of math to arrive at the final result, but a useful result nonetheless. And then the last thing I'm going to say about this before I kind of quit for now and save the rest for another video is that this tau, this factor I've talked about in previous videos, this RC, this time constant for the circuit, you can now see the significance of it and what it means in context. Because when I have an amount of time that has passed that's equal to RC, so when you close the switch and time starts ticking and an amount of time passes equal to R times C, then these functions, these exponential functions that you see, take on the following value. You're going to get e to the negative RC over RC after when t is RC, right? That's going to lead to that, which is the same thing as e to the negative 1. Okay, and so if you kind of do that in your calculator, if you take your calculator and you say, well, what is e to the negative 1? Because that's going to be important in this equation up here, right, after I have a time of RC. And what is, in this equation right here, what is 1 minus e to the negative 1, because that's what matters here. What you find out is that e to the negative 1 is approximately 0.37, and somewhere in that area, and 1 minus e to the negative 1 is approximately 0.68. Right, which is why previously I've said after a time, 0.68, I think it's actually 63. That would make much more sense, wouldn't it? Judging by the math that I've got over here. Yeah. Okay, and so that's why I said in a previous video that after one time constant, after a time of RC, your current is now about 37% of its initial value. You could see that right here, okay, because this whole expression this whole thing becomes 0.37. And the charge on the capacitor, or the voltage across the capacitor, whichever one of these you want to look at, is about 63% of what its final charge will be. Its final charge will, of course, just be this right here, and you're at 63% because you're 1 minus e to the negative 1. And so that time constant is just a characteristic time that we choose to measure. I mean, it makes a lot more sense than just picking some other random time. When is this exponent of e negative 1? And we get this 0.37, 0.63 rule, which is just a nice way to characterize the transient behavior of your circuit. Okay, otherwise, if you want to know the current and the charge across the capacitor, the voltage at any moment in time after that switch is closed, these are your babies. You want to choose the appropriate function to plug in. Finally, as I've said before, all of the math that I just did is very, very similar to what you find in air friction mechanics problems when you integrate when you solve the differential equation that results from Newton's second law. So this is a great time, if you're studying for the E&M test for AP Physics C, this is a great time to go back and in the same day also review the mathematics that comes up with air friction, because I think you'll find that helps you to just kind of solidify this technique of separating the equation and solving it. They really are the same process. It's the same mathematics with just slightly different symbols representing different quantities, but the results are really identical. Okay, I'm going to save the rest for a follow-up video, and in that what I'm going to do is just look at a discharging situation and then a circuit with the resistor and the capacitor in parallel with each other, and we'll write some equations for those as well. All right, take care. Thanks for watching. More to come.